as we get ready to start Chapter 6, Areas and Volumes, this first section, Area Between Curves, you guys might not have noticed a second ago when I was like, oh, stink, I posted all the homework from Chapter 6 all at once. I meant to like schedule some for the future. Did you guys notice that literally that just entailed 1 and 2 and 3 assignments? We have Section 6.1, Section 6.2, and then AP review. Well, book review and then AP review. That doesn't seem like very much, right? This one's due this Friday. This one's due next Friday. Uh-oh. We're going to procrastinate that one, and we better not. It's going to be a rough homework. You have multiple days on purpose. But due this Friday, due next Friday, and the next test is next Tuesday. So it's coming. It's going to be pretty quick. It's going to be pretty fast, but it's going to be pretty packed as well. As we get into Chapter 6, Areas and Volumes, specifically starting with areas, for some of you, the visualization is necessary, and yet it's going to be difficult. I'm going to do as many things as I can to try to not dumb it down, but to give you ways of remembering, give you ways of thinking about it, give you tricks to tackle a problem. Like differential equations, we can't be too specific with. But didn't I say something like, first step, if there's one of these, you should rewrite it like one of these. If there's stuff with plus or minus on one side, you should probably split it up. If there's a dx, maybe you should move him, etc., etc. I gave you tricks for the really tricky ones. I'm going to do that in Chapter 6 also. But some of you, to be frank, will need more than I can give in class. And even though I can do a pretty good job if I get you with a whiteboard one-on-one after school, I can't possibly do that to everyone in CalcAB. And some of you wouldn't ever come in anyway, sadly, even if you needed it. So, to that end, I am reminding you that there are a plethora of calculus tutors online. Not just the colored problems in your book with the QR codes that you can find the videos, but great tutors like CalcAB that has a whole unit on areas and volumes and has great, not test problems, but practice problems along the way that you can actually like try and then answer and see if you've gotten it right or wrong. You have great people like Patrick JMT, I think I have a link to him under helpful links on my website, who uses literally just whiteboards, but I love his explanations better than Con. He just doesn't have as many resources or like the practice problems that you can try on your own or the cool neon colors. But his explanations, I think, are not exponentially better, but I think they are better and more clear and more detailed and more precise. You have, I don't remember her name. Oh, what's she called? I don't know. There's a girl who does a lot of calculus videos too. She's probably in like her mid-20s or so. She kind of has a lazy eye. She's cute, but she has like a lazy eye. Anyway, she has a lot of calculus videos also. She's one that's just come up the last like 2 or 3 years as far as like people using her a lot. But you have some great online tutors, and anyone who online tutors or online does videos of calculus will have areas and volumes, okay? And depending on how they do it, they might have like these really cool computer programs, etc., that might help you visualize so much better than even I can do in class. I do have a few, not in this section, but in the next section, I do have a few like different Wolfram demonstrations. They're called demos. They're even like weird documents. They need this weird reader to be able to see. But I will be able to show you some visualizations, but some online tutors can do a better job than I can in a classroom trying to teach all of you all at once, the general idea. So just a quick reminder, as we go through this, if you're like, I'm just not getting it, don't pretend like you're completely incapable of pursuing learning on your own. You can, and there's lots of resources. Sound good? Okay. So CalcAB is one of them. Patrick JMT is another one. I think even, do I have it at the end of notes? I think I even have a big old page of links. Here it is. Yeah. Especially for section 6.2, because section 6.2 is a bit nasty. I have Patrick JMT's and CalcAB's, but if you guys just remember that I'm saying this chapter is the areas and volumes section. You can find that topic pretty quickly on any of those online tutors. Calculus, help, areas, volumes, you'll find them. Okay, so let's start off with section 6.1. Nice thing is you guys noticed you only have 2 days. We only have 2 days, only 2 class days. Homework's due Friday. The next section we have 5 days, 4 days, and then going over homework questions day. So this one's going to be easier. And guys, haven't we talked about area before this year? Okay, so area is not a new concept, not necessarily, right? Because area, well, that's what an integral always does, true? So if they were to ask us, what is the area between the curves? Oh, come on. Some of you just took the SAT, or some of you have in the past. Guys, what if they were to give you something like this on the SAT, and they were saying something like, hey, why don't you find the area of the shaded region? And they were to give you something like that's X. You would do the square minus the circle. You would subtract whenever you're doing area between, right? So if you do the square, then you would have side squared minus pi r squared. Although you're supposed to be getting this in terms of what? In terms of x. So we have that x is our radius, so I can do that one pretty easy, pi x squared. But what am I going to do for my square? Good, because I need the diameter, right, to be the entire side of the square. And so we have the diameter being that. So we will, wait a minute, 2x, 4x squared. 2x times 2x, and then you would have your expression. And if they gave you like a number, sorry, that's not a y, that's an x, then you could plug in and you could solve. But area between, a couple things I want you to think about just from this super basic, even for SAT problems, super basic problem. When thinking about area between, we have to consider whatever objects, and in calculus, whatever curves we've been given, whatever objects are in calculus, whatever functions we've been given. We're going to have to consider what they look like. We're going to have to consider what region we're going for, what area we're going for. We're going to have to think about them individually, maybe even sometimes taking some broader formula and then applying some particular clue to it, like in this one. Radius is x, side is 2x, like you kind of had to think carefully about not just the geometry, but also how to apply the clue that was given. And then we're always going to have some sort of subtraction when we're talking about area between. So I'm going to go ahead and delete this page. This isn't specifically what we're doing, but the idea is very similar. So if we have these two, area between the curves, what we just saw a second ago was, oh, in your brain, it hopefully for most of you made sense. Area of the whole square minus area of the whole circle will give you what's left. So what if I was just to ask you for this area between, how to find the area of this function, square root of x? Well, first of all, hold on. Don't we need to know like a beginning and an end for area, like when to start and when to stop? So question, how do I even know where to start and where to stop for this problem if it says area between? Yeah. Can you guys see what this word is over here? Natural. The bounds are natural. When I'm talking about bounds, I'm talking about the A's and the B's, right? The bounds are natural. Why are they natural? Because, guys, where does this whole scenario start? At this intersection point. And where does this whole scenario end? At this intersection point. Now, on the graph, can't you guys tell that this seems to be 0 and 1? True? But mathematically, how could we have found that? Mathematically, how could we have found that? How are these natural? Even just like if you don't have the picture, because to be honest, in some ways, even though the picture is helpful, we don't always necessarily know perfectly what things look like when they give it to us. These are basic functions, but not all are. Is there a math way of trying to find intersections? Natural bounds are going to be found by pre-cal, or from algebra 2, or from algebra 1. When we're solving equations, aren't we looking for intersections? Right? When we set two equations equal to each other, when we're solving a system of equations, we're looking for intersections. So couldn't we, and I think, Ryan, you were kind of saying this, couldn't we say, hey, when does x squared equal the square root of x? Does that make sense? Now mathematically, hold on, how do we keep going from there? Say it louder, I'm not sure they heard you. Oh, I thought I heard it. Someone said it. How do we keep going? Square, yeah. I don't think I want a square root of a square root. That's a horrible idea. But squaring, even though you don't like it, x to the fourth equals x, isn't that at least possible to work with? Let's see how good your algebra is. Subtract. Ah! Some of you would divide, and that would be so scary. When we have x expressions on either side, you got to get them all to one side and F-A-C-T-O-R, factor, right? But if I pull subtract x to the other side, you guys okay with me getting x times x cubed minus 1 equals 0? X to the fourth minus x. I know I was running out of room, so I was being lazy. X to the fourth minus x, factor out the common x, and you get x times x cubed minus 1. What happens when we set both of those equal to 0? X equals 0 and x equals plus or minus 1? No. Because adding the 1, cube rooting establishes the signs. So guys, does the picture say 0 and 1? Yeah. But do the functions also say naturally 0 and 1? Yeah. So without even knowing or having any clue what the picture looks like, we still could have gotten 0 and 1 just by finding naturally what? Intersections. Yeah? Okay. Now, let's come back to our picture, though. So we have our intersections of 0 and 1, or I should say we have our bounds of 0 and 1. But I want you to come back to the question I was asking a second ago. Like we did with the square and the circle on the other page, what if I was just to ask you about the area of this guy between 0 and 1? How would we mathematically find that? Good. Just the integral. So let's think about that. Well, if I was to do the integral from 0 to 1 of just this guy, right? Wouldn't it be this entire region, guys? Back from when we first started doing integration, it'd be the whole thing, yeah? Now question, is he the bigger area or is he the smaller area between these two functions? Bigger. So in my subtraction, I'm going to put him first. Does that make sense? So the integral denotes or finds for us area. He's the bigger area. And so like in the problem before when Ryan said the square minus the circle, the reason he did that is because the square was bigger. We want a positive answer for our area between, for the area that we're trying to find. So we want bigger minus smaller. In this case, it'd be square root of x minus, okay, who else do we have? Don't we also have x squared? So how are we going to get our area between? What happens when we take the integral of this guy? Do you guys see what it would end up getting? How's this going to go if I do the pink minus the green? Am I good? Totally. So all I need is the expression, once again, from 0 to 1 of x squared dx. Now here's a math question. What if you didn't have the answer? I shouldn't say that. What if you didn't have the picture? What if you didn't have the illustration? So if I asked you to subtract the bigger minus the smaller, wouldn't you be stuck? If you didn't have the picture and I asked you to subtract the bigger minus the smaller, would you be stuck? Can you guys think mathematically about that question? It's a great question. Why not, Ryan? What could you still do even if you didn't know the picture? What do you mean? So one of our tricks that we're going to use both in this section, mostly in this section, maybe a little bit in the next, is if we don't have the picture, subtraction is still going to accomplish the magnitude of the answer. We just have to be aware of the sign. So as Ryan just said, if you subtracted and solved everything out and figured out that you ended up with a negative, in your mind you just have to realize, oh, at the beginning I guessed wrong. I did the smaller minus the bigger instead of the bigger minus the smaller. But as long as we throw absolute values around the whole problem, don't put them in the integrals. You're going to mess everything up. but around the whole problem, the whole subtraction, solve the subtraction all the way down. Kind of like being clueless. Ignorance is bliss. And at the very, very end, be like, okay, wait, is he negative? Oh, okay. I switched the order, so I just have to make him positive, or is he positive? Keep it the same. Now, guys, technically, can't we combine this whole shabam? Oh, I just lost my white marker. Oh, no, I didn't. If we have common bounds, can't I technically write this as one expression, 0 to 1, right? Of square root of x minus x squared dx. And what Ryan was just saying, just in general, we know we're right on this one. I know that we know we're going to get a proper positive answer for the area between, which is what we're trying to find. But just in case, we are going to throw absolute value bars around every subtraction that we do if we don't have a picture, just to be safe. Just to be safe, because we want it to be a positive answer. Now, guys, this one, once again, said what kind of bounds? Natural. What's different in this picture? We're not going to solve this picture all the way out. If you notice, they didn't even give us functions. I mean, this guy looks kind of like maybe something trigonometric, but let's not worry about who the functions are. My question to you is why, even though it's kind of hard for probably some of you guys to see because it's way over here and it's really dark, and I'm going to make it, awkward, sorry. For those of you that can see the word, what does this say? Given. The bounds are given. Why was natural not good enough in this one? How many intersections do you see? Just one. Could they theoretically intersect somewhere else? Yeah, they could. But number one, it's very possible if this guy got shifted up, it's very possible they wouldn't intersect at all. I know this is a proper picture, so we see that they intersect. But if we were to go looking for when f equals g, intersections, natural bounds, that's not what they want. What do you see that's been shown over here? A and B. So there are going to be times, maybe because there aren't intersections or maybe because of the context of the problem, they only want a certain area, but either way, if they were to give you bounds, well, actually, that's the easiest one because you're like, sweet, I'm just going to use A and B as my bounds of my integral. So I can go ahead and do the integral from A to B of, what's going to go inside, guys? F of x minus, good, because you have to do a subtraction, g of x. Now, properly, you guys technically need to group that whole thing before writing your dx. Just a few of you guys in the Chapter 4b tests on the long answers, you might have seen a little -1 for something like you not writing a dx or you not writing parentheses. Now, maybe it was just -1/2. But remember, the AP guys, if they see something improperly noted or notated, they're going to take off points. Okay, we have to keep it legal, have to keep it proper. But guys, why did Patricia say f minus g? I heard her first. Why did she say f minus g? She's saying f's bigger, and what does she specifically mean? The y values of f are higher, which means his area from the function to the axis is going to be bigger, right? But just in case, what if we didn't fully know? What could we still do, like Ryan was saying? Booyah. Does that make sense? Okay, so that's building up to where we're going. Let me go ahead and get some more lights on. Maybe we'll get back to a cool black screen. Maybe we won't. There we go. And Colby can see a little better too. I don't know why I have that line so long. Give us a little bit more room. There we go. So what's the purpose of this entire section? To find the area between two curves, usually with natural bounds. And if it's with natural bounds, we're going to go ahead and go looking for intersections. And so intersections, remember, we're setting f of x equaling to g of x, and then we're solving. But I'm going to say solve with the word I'm really afraid from algebra that we're not so great at, or we try to ignore as much as possible, but we can't. Factoring. Like you saw with the x to the fourth and the x cubed. Like you saw with the x to the fourth and the x cubed. division would not have been a good option. You would have found one solution, but we need, especially for these, to find as many possible intersections as we can. Now, we're going to have to deal with, well, what if there are more than 2 intersections? Uh-oh. But for right now, we set them equal to each other and we solve. So we're going to have some algebra right up here with factoring. Sometimes defined bounds, you can say, well, or you can just even underline given, right? Given. Either you're given a picture and you're finding A to B, same thing. Either you're given a picture and so you look at what's shaded and you say, okay, cool, A is this and B is this. The x-bound is this on the left and the x-bound is this on the right. Or you're actually given words like from A to B or something like on the interval A comma B. There are different ways to give you the bounds, but either way, we need to know what bounds to use. But even beyond knowing what bounds to use, that just is how we set up the integral. Then putting in our integral. One way is to visualize. One way is to visualize. And visualizing, we need to figure out which one is most positive, aka which one's biggest. And we'll do the biggest minus the smallest, and it'll be positive, and everything will be happy, and butterflies are flying around like yesterday on the track, so I heard. And everyone's going to be great and dandy. However, if we don't visualize, or if we can't visualize, like Ryan and Thomas were talking about just a second ago, we're not stuck. We might just have to think of something else at the end. So after we figure out which one is most positive, we try to visualize, but at the end, worst comes to worst, we do some sort of subtraction. Somehow we try to think of f of x minus g of x, f of x being the bigger, g of x being the smaller, depending on the case. We make this our integrand. We put this in with a dx and with our integral from a to b. As we make our integral, we're going to have to know our bounds, and so we have to think about, okay, is it natural? Is it defined? Fit in. If it's natural, go find it. But number 3 says, must split up integrals if the curves ever switch orders. Wait a minute, where in calculus with integrals have we ever had to split them up? Like they were given to us from A to B, and we had to say, oh, wait, no, we have to stop at C. Do you guys remember what we were doing? Absolute value. So that's where Ryan's thing comes in. If we do go throwing in an f of x minus a g of x, and if we do technically, now here's where it gets tricky, if we're not able to visualize and we're not able to see if there are multiple branches, multiple intersections, multiple pieces we're adding together, we do technically need to think about this as an absolute value on the inside from A to B. And just like we did with absolute values, we're going to have to split up at any x equals c where f of x equals g of x. If it ever happens. Now, if you can see the picture and if you can see that there's no extra intersections between A and B, it doesn't matter. Pull those absolute value bars out, do the subtraction inside the integration, do your antiderivatives, plug in, see if it's positive at the end, see if it's negative. If so, switch it. But we will have to split up if we have any intersections C's or D's or E's in between A and B. We'll have to split it up. Otherwise, our orientation would be wrong. So we'd have like a positive number and a negative number and a positive number all put together before we ever get to the positive negative consideration step. So you can just kind of think absolute value. We've always had to do that. Except I think in our card, you guys have a forever card for that, right? In our card, I don't remember if we actually said set f equal to g. Find the intersections. I think we said something like find the zeros. But either way, aren't the intersections when they're equal, isn't that the same thing as the zeros of the subtraction? So either way, finding the zeros according to our absolute value card will be when f equals g, will be the intersections. So with that, what if I was to give you something like this? You can try to visualize, or you can just tackle it mathematically with a formula and say, I'll figure it out later. You can try to visualize. I put a graph there in case you want to try to. or you can mathematically go straight to the formula. I'm giving you guys just a few seconds in case you want to get ahead of me and you want to try something on your own. But don't worry, I'm not going to give you guys tons of time because we haven't really done many examples yet. And we haven't done any where there hasn't been a picture yet. Some of you, when I said try to visualize, some of you were like, well, these are basic graphs. I think I'm supposed to know them. So then there's one. Got it. And then here's another. Did anybody just get confused, though, if you tried to visualize? Depending on how accurately you draw your graph, you might not actually see the area they want you to find. Do you guys see any area between? Now, if I start shifting it, yeah, but do you see any area between? But wait a minute, who's supposed to be steeper? X squared or x cubed? If x equals 4, 4 squared is 16, x cubed is 64, who's supposed to be on top? The green. Okay, so my picture's wrong. My picture's wrong. Let's figure out what the picture is supposed to look like by doing the math. Guys, they didn't say from A to B, which means these are natural bounds. Natural bounds, how do we find them? Intersections. So x squared equals x cubed. Wait, does this ever happen at 0? That's what my picture showed. It happens at 0. Oh, but where else does it happen? Would you guys have subtracted? Would you guys have pulled out the common factor? And would you have realized this happens at 0 and 1? This is all just asking, hey, what are my bounds? So if I plug in 0, 0, 0, they intersect. And if I plug in 1, 1, they intersect. And I know green ends up faster eventually, so he has to be going pretty steep. And red, interesting, ends up going slower. Wait a minute. Now, even though this is a horrible picture, why does it make sense that x squared would be bigger in between 0 and 1? Choose something like a half. What's a half squared? A fourth. But what's a half cubed? Almost an eighth. But either way, if you cube a little baby fraction, he's going to be smaller than if you square it. So just for a little while, x squared gets to win. But then for all the numbers bigger than 1, x squared loses. Some of you might not have realized that. Now, my picture isn't great anyway. I apologize, it's a little bit nasty. But if I had done this a little bit better. There is an area between, but most of you, if you graphed this just naturally, you wouldn't have known it unless you went over here and did the math and said, oh, wait, 0 and 1. Now, I do have my picture, but let's say, we had done the whole like, oh, x cubed is always on top. Let's say we had done it x cubed minus x squared. Just kind of like ignorance is bliss. We're going for it. Our only intersections are 0 and 1, so we don't have to worry about splitting up. There's not like 3 intersections that we would have to split up. So we're like, okay, cool, we're good. We can do Ryan's trick of an absolute value on the outside, or we could just say, no, I'm pretty sure I'm right. Now, guys, how would you actually solve this problem? Oh, silly goofs. It's just an integral. How would you solve it? Yeah. What's your antiderivative? 1/4 x to the 4th minus 1/3 x cubed. And we're going between 0 and 1. Okay, cool. So let's plug in 1, and we end up with 1/4 minus. Let's plug in 1, and we get 1/3. And then that's f of 1, f of b, antiderivative of b, minus. It's time to plug in 0. But 0 minus 0 is just 0. Oh, 1/4 minus 1/3. Box it. You're done. Wait, pause. That would be wrong. Not because your antiderivative is wrong, not because your plugging in is wrong, but because your orientation is wrong. Who's bigger, a fourth or a third? A third. Is this, ooh, careful. Would you rather a fourth of a pizza or a third of a pizza? Well, if you're on a diet, that one. But if you're not on a diet, that one. He's the bigger one, which means this value is negative. So if we were sticking it to the man, we would have to put an absolute value around it. Another way of looking at it is if you were to actually solve, you would have ended up hopefully getting common denominators. We're not that bad, right? 3/12 minus 4/12 is negative 1/12. This is where we say, oh, we made a mistake. But now we can say all of those are equal. Thank you, Ben. Now we can say all of these are equal. Now, if we just put absolute values here, technically the AP guys could take off points and be like, an absolute value there doesn't equal a non-absolute value here, so be careful. If you do Ryan's trick of throwing in an absolute value, we have to throw it in everywhere. But we're not throwing it in different pieces. We're not changing all the minuses to pluses. We're doing this whole problem, doing this whole subtraction, and then saying, okay, now absolute value. The final answer is 1/12. But pause. What if this was a calculator problem? What could you have done? Besides like graphing and looking at it, what could you have done? Don't you guys have a really cool function that takes an integral for you? So maybe your only job would have been to set up the integral and then just do one of those cool like FRQ things straight to a decimal. Does that make sense? Cool beans. All right, area between natural bounds. Oh, let's get a card. Uh-oh. Uh-oh. Did something weird just show up on the card? One thing should look very normal and one thing should look kind of flipped on end. The first one says top minus bottom, which is all that we've been seeing, a top curve and a bottom curve. Everything is in terms of x. An x bound to the left, an x bound to the right, an x value to the left, an x value to the right. Function in terms of x's minus function in terms of x's. Booyah! But what else do you see could be necessary? Now, in this little region that I showed you, the area could be found top minus bottom. Thinking about how if everything is in terms of x, we're measuring from one x to another, and we're measuring down to the x-axis. There actually is, and I haven't really geometrically, well, visually shown you what's going on when you have a dy. You guys have solved them. I've made sure that you've seen them with dy. But what's going on when you have a dy is you're actually measuring side to side curves to the y-axis for area, from a y lower bound to a y upper bound. So actually both of them are appropriate, both of them are good. And this is our, forever card number, where are we at? Stink, integration is net change was our last one. Is it 40 even? Was that 39? $43? $43. So integration as net change is 42. Whew! But if you guys notice, split up the integral if intersections occur between bounds. Pretty much, kiddos, this is the entire forever card for all of section 6.1. Some of you should definitely start homework tonight. But with that y thing, it might get a little weird sometimes. All right, guys, we're good. Make sure you have everything on your way out. Otherwise, don't forget your circular treats for tomorrow that can be shared, not just for you, or else just you will enjoy it. Bye, guys. Keep going. You got this.